Oh baby, this is number 101, probably the hardest problem you're ever going to encounter in all of physics. It's here in living color. You've got this system and it says figure out the acceleration of the block. So you have to kind of start with the forces. Well, this is gravity. Well, I don't want to put it there. I'm going to put it down here. You take 8 times 9.8 and you get 78.4. So then so what you're going to do, let's see here. I'm going to end up breaking this into the force perpendicular and the force parallel. So there's also the normal force. There's a pull happening right here. And then on top of all that, then there's friction. Holy crap. So there's 4 forces acting on this: gravity, pull, normal, friction. And they're all kind of related somehow. Well, first of all, the pull comes from this 16 right here. And if you take that times 9.8, you get 156.8 newtons. That's the force of the pull, 157. The normal force, let's see here. So I know this angle is 37 degrees. Through a little clever geometry, this is 37, then that means that this has to be, let's see here, 90 minus 37, 53. So then this has to equal 9, so that's 37. I'm going to use the sine and cosine to find these. So I'll say the sine of 37 degrees is equal to the opposite, which is the force parallel, divided by the adjacent, which is, or the hypotenuse, which is 78.4. So opposite over the hypotenuse, which is 78.4. So the force parallel, you can do that on your calculator, comes out to 47.2. And I'll do the cosine of 37 degrees is the force perpendicular, because that's the adjacent over the hypotenuse. So the force perpendicular comes out to be 62.6. So I'll write those in. 47.2, and this is 62.6. Alright, so now I know the normal force. Well, because this box doesn't float up into the sky and it doesn't dive down into the inclined plane, so this has to be equal to 62.6. Now I can find friction, because the force of friction is equal to the coefficient times the normal force. So the coefficient is 0.23. The normal force is 62.6. So if I multiply those together, I get 14.4. So that's my frictional force, 14.4. Now, my drawing's a little bit too busy right now, so what I'm going to do is make a new drawing just to kind of simplify stuff. I've got my box again. I'm being pulled this way at 157. I'm being pulled this way at 62.6. I'm being pulled this way at 14.4. I'm also being pulled this way at that's 47.2, and then I'm being pushed this way at 62.6. So we've got competing things here. This one and this one cancel. So we actually have a net force. Like, the rope pulls it up at 157, and gravity and friction pull it backwards at these two. So I can find my net force. That's 157 minus 14.4 minus 47.2. So the net force that's acting on this thing is 24 newtons. 24 newtons uphill, right? Because the pole has to overcome gravity and friction to get it to move up, and it actually does. It's 24 newtons more. So I can find the acceleration now. Because use the net force, because the net force is 24. The mass. Now this tricks a lot of people. It's not only the 8 kilogram mass that's moving, it's both of these masses, the 8 and the 16. So you have to use both of the masses in your equation. So 24 equals 20. Well, that's not right. Oh, this is, dang it. This isn't 24. Shoot, I did my math wrong. 157 minus 14.4 minus 47. That's 95.2. I made a mistake. So this is 95.2. And then I take 95.2 divided by 24. Okay, this is getting easier now. And you get 4.0. So that will tell you the acceleration, and that's uphill. You should definitely make sure you should say that, because that's important. Now, to figure out the tension in the rope, you have to. What I'm going to do is I'm going to look at one of the boxes in particular. I'm going to look at this box. This is the box that was 16 kilograms. So what's happening is it's accelerating this way at 4.0. So gravity pulls it down at the 157. And then there's the string pulling it up. This is just like the elevator problems from last chapter. So you're going to use F equals ma. Make sure you use the net force, because the net force, we got two forces here, 157 in the string. So I'll actually call positive down, so I have 157 minus the force of the string, and that equals the mass, which in this case is 16, and the acceleration, which is 4. So you take 16 times 4, and that comes out to be 64. So then you subtract 157, you get negative F of S equals negative 93. So the force in the string is equal to 93 newtons. It's a positive 93. Now, why did we not use... A big question I always get is, why did you use 16 here and not 24? Like, how did you have to use it here? Well, I was actually just looking at this system, because this one, true, goes down at 4, and it's being pulled by the force of the string, right? And that, because it slows it down a little bit. So you're only looking at this system, so the answer, you only use that mass. But when you're looking at both of them, they both move together, and so on.